Well, let's start off by, I'd like to start off by introducing myself. My name is Lance Zurich, and I am the product manager for the Fischertechnik division at Studica. And today I'm going to give you a brief overview of the Fischertechnik STEM Prep 2.0 and STEM engineering sets. And these sets were designed to enable educators to provide students with a project-based standards-focused curriculum program, which involves inquiry, design, and problem solving. And the curriculum for each of these sets was created especially for Fischertechnik by noted educator and STEM expert, Tom White. So most educators are well aware that the term STEM is an acronym, which the letters of which stand for science, technology, engineering, and mathematics. Now, if you've been involved in any aspect of education, you probably can't open your email box without seeing STEM highlighted in the subject line of at least one of your daily messages. And you certainly can't read an educational journal or visit an educational conference when such things are possible without being bombarded by references to STEM. And the reason for this is, of course, quite simple. To quote the bipartisan Congressional STEM Education Caucus in their report on the importance of STEM education, STEM education is necessary because it helps provide the scientists and engineers that are needed for future development. It provides the future workforce with the skills required of a high-tech world, and it builds the foundation for scientifically literate voters and citizens. As such, STEM education could really be considered as a matter of national security. On every level, the world around us is changing at a frantic pace. STEM education, it could be argued, enables us both as individuals and as a nation to understand and keep up with these rapid changes in technology, changes which in turn are altering the demands and scope of industry. And obviously, if we as a nation are to keep our stature and position on the world stage, this requires us to keep pace with the rapid developments occurring around the globe, where countries such as China and India are making major investments in state-of-the-art infrastructure. And while, of course, all that's well and good, and we should all, of course, strive to be good citizens, some students might also ask, so what's in it for me? Why do I want to study engineering, or why do I want to study coding, or what have you? So let's consider what it means on the individual level. Well, first off, a few years back, the United States Department of Commerce released a set of projections for the decade leading up to 2018. Now, these projections had indicated that STEM occupations were expected to grow by 17%, compared with 9.8% growth for all other occupations. Now, in March of 2017, the Office of the Chief Economist released a STEM Jobs 2017 update, which basically took a look at how these numbers were playing out up to the year 2015, at this point with three years still left in the initial projection. Now, what they found at that time was that while the projected STEM growth, and once again, this is just up to that point in 2015, was as expected, up significantly, albeit just a slightly bit less than they expected to reach in total by 2018. So what they found was that it was up 14%, still on the way to that 17% they were looking for. But by comparison, the actual growth for non-STEM jobs, which again, they expected to reach 9.8%, had instead at this point only reached a fraction of the growth that was expected, just 1.7%. So a real stark difference there. Now, here's a statistic that I like to share that should give anyone entering the job market a future pause. And this comes from J.D. Chesloff in his Education Week article from March of 2013. To quote Chesloff, across the country, across all occupations, there are 3.6 people for every one job. In STEM fields, there is one person for every 1.9 jobs. Employers can't find the talent to fill these jobs, which is even more surprising considering that the U.S. Census Bureau recently reported that the median salary for engineering majors was the highest of any profession, end quote. Now, as Chesloff goes on in the article to state, quote, supply is low and demand is high. There is a mismatch between projected future jobs requiring STEM skills and the projected supply of qualified workers to fill them, end quote. So going back to the STEM Jobs 2017 update released by the U.S. Department of Commerce, which I referenced a few slides ago, here are 3 key points mentioned in this report that are well worth keeping in mind when considering the importance of STEM education to the worker. Key point 1, STEM workers command higher wages, earning on average 29% more than their non-STEM counterparts in 2015. Key point 2 relates to the fact that many graduates with STEM skills may not always end up in what are strictly considered to be classic STEM jobs. These would be things, of course, like scientists or engineers or what have you, things we always think of. Quote, STEM degree holders enjoy higher earnings, regardless of whether they work in STEM or non-STEM occupations, end quote. Now, there was a video I saw a little while ago on YouTube posted by the Women's Foundation, or excuse me, the Women's Forum for the Economy and Society. And the title of that video I thought really summed things up nicely. And that was, every company is a tech company. So essentially what I take from that, and what I think students want to keep in mind, is that whatever a company makes, whatever a company sells, or whatever service it performs, at some point, STEM skills are required to help that company fulfill their mission. And moving right along, key point number 3 relates to job growth. Employment in STEM occupations grew much faster than employment in non-STEM occupations over the last decade, 24.4% versus 4% respectively. And STEM occupations are projected to continue to grow by 8.9% from 2019 to 2024, compared to just 6.4% growth for non-STEM occupations. Now, the trick for educators is to find methods for getting students involved in STEM, and in particular, involved in the most highly in-demand technology-focused skill areas. These would be things such as engineering and coding, and to do so in a way that engages the students' interest and creativity, while at the same time developing the work habits, the way of approaching problems, and the skills that students will need to draw on as they move forward in their careers, both academic and in their working lives. Now, most experts agree that one of the most effective methods for teaching STEM is by providing exercises where certain results will occur and students have to discover why they occurred, or where students have to find a way to achieve a specific outcome. They do this through experimentation, through research, and through trial and error activities. In short, they find the answers to these questions through the use of hands-on, project-based learning. And that brings us to the focus of this webinar, which is the Fischertechnik STEM Prep 2.0 and STEM engineering sets. Now, both of these sets have been designed to provide a guided, project-based learning experience, complete with detailed, standards-focused curriculum using the unique Fischertechnik building system. So that might bring up the question, what is Fischertechnik? Well, just to provide you with a little bit of background, Fischertechnik is a flexible and innovative construction system. Now, unlike other popular construction sets that are designed to simply stack, Fischertechnik was created with more of an engineering mindset. The core building block of the Fischertechnik system is unique because it allows attachment from all 6 sides, and because of this, it allows for almost limitless design possibilities. Now, many of the parts are designed to slide together and lock in place using a tongue and groove assembly method, and the hundreds of different parts available will also help to address very specific design needs. Fischertechnik was created back in 1964 by German inventor Arthur Fischer, who noted for countless innovations used in both the construction and the automotive industries. Mr. Fischer, at the time of his death in 2016, had amassed more patents in his name than Thomas Alva Edison had amassed during his own lifetime. Now, besides Fischertechnik, Mr. Fischer was the inventor of synchronized flash photography, and that was back in 1949. And he was also the creator of the expanding nylon wall plug, which is used in conjunction with a screw or a bolt to help anchor heavy objects to walls. His company, the Fischer Group, employs thousands of individuals worldwide, producing many variations of fastening devices used in building construction, as well as various components used in the automobile industry. And they also provide consulting services in regards to various state-of-the-art manufacturing processes. We would also like to mention that Fischertechnik was the very first construction set to offer students the ability to build and program their own robots. That was using the original pre-Macintosh era Apple computers. Now, almost since its inception, Fischertechnik has been used by middle schools, high schools, colleges, and universities all around the globe to explore STEM-related concepts. And these are going to be things like robotics, renewable energy, mechanics, optics, physics, pneumatics, and so much more. Fischertechnik has also been used by numerous companies, including companies like Porsche, Daimler Chrysler, and BMW, just to name a few, for industrial simulation and training purposes. In addition, over the last few years, Fischertechnic's line of pre-assembled simulation models have found wide adoption for demonstrating and exploring the world of IoT, also known as the Internet of Things, where industrial processes can be monitored and controlled from the cloud. As such, more than just being something that students are only going to use for a year or two in their development, instead you can think of Fischertechnik as being designed so that students can grow along with it. Essentially, as students progress through their academic careers, they can also progress through the levels of Fischertechnik education solutions which are available. The Fischertechnik STEM Prep 2.0 and STEM engineering sets are two of the most important members of the Fischertechnik education family. STEM Prep 2.0 is designed for exploring essential aspects of technology with a focus on physics, robotics, energy, and power. STEM engineering is designed to provide a comprehensive overview of robotics, coding, and automation systems. Each of these STEM-focused sets is designed to provide all the materials that you will need, and by this we mean both the physical and the instructional materials, to enable teachers to offer a complete, daily, STEM-focused classroom experience. STEM Prep 2.0 contains over 75 academic hours of curriculum material, and STEM engineering contains over 150 academic materials. So essentially, if you offer your students a STEM education class of a single 50-minute period each day for 5 days a week, this would provide you with enough curriculum material with the STEM Prep 2.0 set to cover a half a year, and with the STEM engineering set to cover a full academic year. The curriculum for each of these sets comes in a handy PDF format. There's a curriculum PDF specifically for the teacher to conduct the class, and also a separate PDF that can be shared with students, acting as a guide for the class activities and helping everyone to stay on the same page. And to assist new users of the Fischertechnik system, the curriculum also includes a helpful tutorial section. This section provides guidance on identifying the many types of parts included, it shows how these parts fit together, and it walks the user step by step through the building of a simple model. The STEM Prep 2.0 and STEM engineering sets are also designed to be somewhat dual function. Now, besides being designed so that educators can conduct a curriculum-centered project-based STEM class, they also include full-color step-by-step assembly manuals in PDF form from various popular Fischertechnik education sets. Now, these assembly manuals can, of course, be used as a reference when students will be creating their own original projects, which they will do during the course of both of these curriculum programs. But they also allow you to build all of the models shown in each of the manuals with the parts included in each of these sets. In fact, the STEM engineering set allows you to build all of the models found in Fischertechnik's 3 most popular robotics sets. And the STEM Prep 2.0 allows you to build all of the models found in 8 different STEM education focused sets, as well as the robotics BT beginner set. And we're going to discuss all of this a little bit more just a little bit later. Now, as mentioned at the very top of the presentation, the curriculum material found in the Fischertechnik STEM Prep 2.0 and STEM engineering sets was created by a man named Tom White. Now, Tom is a noted educator who has been involved in STEM since the 1970s, known for designing programs for educational institutions and for industry. In fact, as an expert in hardware and software integration, Tom was pivotal in introducing CAD, CAM, control systems, digital control, additive manufacturing, and other such topics to the classroom. Now, currently, Tom is the Director of Technology for Currently, Tom is the Director of Technology for STEM curriculum at the globally recognized industrial manufacturing company, Siemens. Now, this is not the first time that Tom White has created a curriculum program around Fischertechnik. Now, besides also being the creator of the curriculum used in our elementary-focused Introduction to STEM series, and our other project-based offering, the Robotic Competition Set, both of which are the subject of their own webinar presentations if you were interested in finding out more about those. Now, besides that, Tom has incorporated Fischertechnik in many of the educational programs that he's designed over the years. And when I've talked to Tom, he's often said that he believes that Fischertechnik is the ideal construction set for any kind of engineering-based curriculum program, and he's got several reasons for that. First, he likes that the materials can be used and reused. Things that are built can be taken apart and reassembled into something completely different. He also likes the versatility of Fischertechnik and the fact that it offers so much more economy than, let's say, just purchasing an expensive piece of equipment. For example, something like a robotic arm, where you might only use it for a few experiments and then it sits on the shelf till next time around. And he also appreciates that the Fischertechnik system, with its wide assortment of very specific mechanical and structural parts and components, offers almost limitless creative opportunities for engineering students. The curriculum for both the STEM Prep 2.0 and the STEM engineering sets has been designed to address some of the most widely recognized academic standards which are currently in place. And this includes the college and career readiness math standards for math, or excuse me, college and career readiness standards for math, science, reading and writing, the NSES content standards for technological literacy, the ISTE standards, and the next generation science standards. Now, the goals of the curriculum. Well, when Tom White put together the curriculum for these two sets, he had several goals in mind. First, based upon his observation that various types of teachers have different strong points. For an example, he sees his own strong point as being more in the creation of curriculum material such as this, more so than it would be in him conducting a lecture. With this in mind, he focused on creating a curriculum that would provide a broad foundation of tools for all types of teachers to be successful in providing in this class, so they could instead focus on the needs of the students. Materials have been included at the beginning to familiarize new users with how the system works, and each section of the curriculum clearly spells out how things will be covered in that unit. Essentially, this was designed as a turnkey solution that would provide everything teachers will need in one place. Now, in short, the curriculum was designed to provide a clear roadmap for both the teachers and the students, with the learning facilitated through the extensive use of projects and problems for the students to address. The goal was also to enable teachers to provide students with engaging curriculum-based projects that had an authentic objective in solving real-world problems and which contain embedded academics. The detailed curriculum with each of these sets, if followed, will allow educators to provide what is essentially a standalone project-based STEM education class. Of course, as mentioned before, each set also includes step-by-step instructions for building the models found in various topic-focused Fishertechnic sets. And under this project-focused model, students are told upfront what they will need to learn and understand. They're given a real-world scenario where they take on the role of a professional working on a team, which has been presented with a design challenge that they must devise a solution to, and then are provided with different tools and different pathways to help them achieve this goal. Now, among other things, students will be asked to perform research. And by this, we mean research both inside and outside of class. And they're going to have to learn the documentation process. And this will include things like designing or creating a design brief and maintaining a digital engineering journal. Students will also be required to collect data. They're going to learn firsthand how data acquisition works. They're going to learn how to process data, how to put data into graphs and other formats, and so on. Students are given a technical literacy task driven by the project. Fulfilling this task will require them to gain the knowledge and tools needed to address it through research and exploration. Students will perform a series of specially designed enabling activities through which they will acquire the necessary science, math, and tech-based skills to successfully complete the project. They will devise solutions to their tasks and create prototypes using the advanced Fischertechnik modeling system. Where required, students will also create and install the programs needed to control their prototypes. They're going to again document every step of the entire process and formally present their findings, including a demonstration of the prototype. Now, at this point, let's look at the sets themselves. And we're going to begin with the Fischertechnik STEM Prep 2.0, which you see on the screen right now. The prep in the name, like STEM, is an acronym. In this case, it stands for Physics, Robotics, Energy, and Power, which again are the subjects focused on in this set. Each of these sets is designed to be used by a team of 2 students at a time. The set itself contains 2,260 parts and components, including the RoboPro LT software, the BT or Bluetooth smart controller, an electronic module, a pullback motor, a solar motor, an excess motor, a mini motor, a compressor, 2 solar modules, a gold cap energy storage unit, an NTC resistor, a phototransistor, an LED, 2 rainbow LEDs, and many other parts, all of which come packed in a sturdy grapnel storage box. The project themes addressed in the STEM prep set include the following: sketching and documentation, simple machines, mechanical systems, structures, conversion and storage of energy, electronics, optics, digital communication, and programming control systems. And again, the curriculum for the STEM Prep 2.0 is designed to provide enough material to cover 75 plus academic hours. The STEM Prep 2.0 set also includes step-by-step pictorial instructions culled from 9 different Fischertechnik sets. And these include the drive system set, eco-energy, pneumatics, mechanics, physics 1 and physics 2, electronics, optics, and light, and the robotics BT beginner set. Now, the one thing you see a little asterisk by the eco-energy set. Aside from 5 models shown in the instructions for the eco-energy set, which incorporate the optional fuel cell add-on, which can be purchased separately if you so chose, all of the other 118 models shown in these instruction booklets can be built with the parts found in this one set. Now, as such, with this in mind, even if you didn't wish to use the curriculum itself for whatever reason, the STEM Prep 2.0 set would still be a very convenient and a very affordable way to have the building and learning options from these 9 sets in one box. Moving right along, next we're going to look at the Fischertechnik STEM engineering set, which you see on the screen now. This set, which can be used either as a follow-up to STEM Prep 2.0 or totally on its own, is designed to provide students with a comprehensive overview of robotics, coding, and automation systems. The set is designed, again, for use by teams of 2, but in this case, even possibly up to 4 students at a time. Now, the reason this differs on the other set is because the projects here are a little more elaborate, and they're going to involve many more steps than many of those projects found in the STEM Prep 2.0 curriculum. With this in mind, it's easier to keep a higher number of students actively engaged with the research, the programming, and all the other aspects that are going to be required for each of these projects. The set itself contains 890 parts components. In this case, it includes the RoboPro software, the robotics TXT controller, a Fischertechnik AccuSet, which is a rechargeable battery pack with a charging unit, 2 encoder motors, a compressor, 2 phototransistors, 2 excess motors, a mini motor, 6 push-button switches, a color sensor, an NTC resistor, 2 LEDs, 2 solenoid valves, a vacuum suction device, and hundreds of other parts, once again, all of which come packed in a sturdy grapnel storage box. The project themes covered in the curriculum for the STEM engineering set include the following areas: sketching and documentation, basic electricity, programming, sensing and vision systems, mobile robotics, actuators, and the fundamentals of automation and robotics. And again, as you see, the curriculum itself is designed to cover 150 plus academic hours. Now, there are also activities included to address the following areas that come up during the course of the curriculum: sketching, schematics, Ohm's law and power, an introduction to using the RoboPro software and to using the TXT controller, working with flowcharts, working with open loop and closed loop programming, learning about digital branching, edge trigger versus level trigger, logic gates, combinational logic, analog branching, variables, subprograms, data, sensors such as the digital switch and the digital phototransistor, analog sensors such as the NTC resistor and the color sensor, learning about the camera attachment, using the camera to detect motion, working with color detection, creating a ball finder, which involves using the camera as a vision system on the robot, working with the line tool, learning about encoder motors, building the control panel, pneumatics, working on positions, recording positions, and utilizing existing programs and subprograms. Now, this set also includes step-by-step assembly instructions found in the following the following three Fischertechnik robotic sets: the Robotics TXT Advanced set, the Robotics and Electro-Pneumatic set, and the Robotics and Industry set. So once again, even if you wanted to work outside of the curriculum, this set will still contain all the parts, the software, the controller, the power supply, etc., so that you can build any of the 22 models found collectively in these three sets. And this was going to include things like color sorting machines that you're going to be able to build, pinball machine simulations, various mobile robots, robotic arms, and many more. Now, at this point, as we've touched upon what's covered by each of these sets, I think it's going to be most useful to show you exactly how the curriculum for the STEM Prep 2.0 and the STEM engineering sets is structured. Each unit of both the STEM Prep 2.0 and the STEM engineering curriculum contains a roadmap of sorts where each of the following elements are addressed: the purpose, the concepts, the student deliverables, assessment and evaluation materials, an outline, the standards, an authentic project scenario, a daily teaching plan, supporting activities, and resources. To put this into better context, let's look at the curriculum that accompanies the STEM engineering set. Now, again, while we're going to focus on material only found in this particular set, the structure of the units and how subjects in both the STEM Prep 2.0 and the STEM engineering curriculum are addressed is essentially the same for each. Here's the table of contents for the STEM engineering set. Now, the first thing I'd like you to note is that before we get into the specific units, and if you look closely on this page, you're going to see that there's going to be listings for sketching and documentation and basic electricity. But before we get into that, there's a section that's designed to help any new users of the Fischertechnik system to quickly get up to speed. Again, the core building blocks in the Fischertechnik system are designed to attach from all 6 sides, and many other parts are designed for very specific purposes. Now, as this is different than the simple stacking construction of many other building sets you may have encountered, we've included this section right up front to help increase your comfort with the system and to allow you and your students to get the most from your building experience. As such, there's a section showing how the parts fit together and discussing the pin and groove assembly method that's used. There's a section showing you how to identify the various different parts from the core building blocks to more specialized parts such as clip axles, girders, rivets, angle pieces, and much more. There's a section that shows you a picture of every part contained in each set, along with the name, the part number, and quantity of the part that are included. Now, this can be especially useful if you ever wish to order additional quantities of any parts to add to your assortment. And also, for those educators who might be new to the approach that's used here, there's also a chapter discussing how to go about conducting a project-based STEM education class. Now, on that note, let's jump ahead to a sample unit just so we can explore the structure of what we discussed. This unit, as you will see from the image on the screen now, is focused on programming. And the picture you see at the top of the sample page is a graphic representation of the RoboPro software. Now, as you'll see in this close-up, RoboPro is designed to utilize icons to represent the different actions the robot must perform, which students arrange in a flowchart style manner to create the program for each robotic model. Now, the nice thing about using graphics programming software such as RoboPro for programming is that it allows students who may not have any prior experience with programming of any sort to quickly become comfortable with doing so. And at the same time, it also helps to familiarize them with the core concepts that will be found in all types of programming. Now, going back to our main page, as you will see right under the unit title, the first thing that we're going to encounter in each unit is a section entitled The Purpose of the Project. Now, this is the section that seeks to clearly spell out to students the answer to that eternal student question, why are we doing this? So, see, too often in the past, students might encounter subject matter that just didn't seem to have any relevance to them. I know for myself, when I was in high school, would have been a subject like trigonometry. Well, in this case, students are told why the material is necessary and where it fits into larger scheme of things, and basically we'll hope to develop here, what we hope to develop here. It basically makes it relevant to them. Next, you will see the concepts to be addressed in this unit. And these can be thought of as the big ideas that students should take from this project that will be essential for them to understand and utilize, not only today, but also to hopefully draw upon as they move forward in STEM fields of study and STEM-related careers. Following this, we have the outline. Now, in this section, we drill down more specifically to what's going to be addressed in this unit. Now, again, as the particular section we're looking at is on programming, you're going to see that we're going to touch upon areas such as methods for writing programs, including flowcharts, word problems, and so on. Working with program characteristics, for example, open or closed loop. Working with branching, digital branching, analog, subprograms, and so on. Next up, we come to the section where each of the specific standards to be met by this particular project unit are spelled out, which of course will help provide the educational justification for the project they're going to be doing. Because it's impossible to include all of the standards that have been created by individual states and school districts, even though we're often asked about this, what we've done instead is we've selected the most universally accepted standards that are currently in place in the United States today. With this in mind, we begin with the college and career readiness math standards, which are followed by the reading standards for literacy in history and social studies, as well as the writing standards for literacy in history, social studies, science, and technical subjects. Following that, we have science standards, beginning with the NSES content standards for K-12 and the standards for technological literacy, which are then followed by the ISTE Foundation standards for students and the next generation science standards. After this is an assessment section, which includes links to both general course rubrics as well as rubrics related to the specific unit. After this, we have the essential question. The essential question can be thought of as the broad major idea that's going to be explored in this unit. Now, in this particular case, the question being put forth is, how can we make decisions electronically and remove the need for human intervention? And after that, we have what might be considered the centerpiece of each of these units, which is the student scenario. The student scenario for each unit gives the students an opportunity to explore the unit's essential question, and this occurs in the form of a real-world problem that students are given to solve, which helps to provide a tangible example of why the subject matter being explored is both relevant and important to understand. Now, in this particular example from the programming unit again, students assume the role of a controller/programmer who happen to be working at a programming company that specializes in designing elevators and writing the control packages for these elevators for their clients. Now, again, students will be working in small groups, which again is the way all projects are approached in the course of the curriculum. So working in these small groups, students are asked to work together to design an elevator that will have certain parameters and must be able to perform certain functions. One example of this might be if you had an elevator that was at rest on a middle floor and someone were to push a call button on a lower floor at the same time as someone pushed a call button on a higher floor, you have to basically create a protocol in the programming to address which call button the elevator answers first. Again, in the student scenario, the client's requirements are all spelled out, and the students will be required to, again, design an elevator, create a program to address these specific requirements being put forth, build the actual elevator prototype using Fischertechnik, and eventually prepare a presentation for these fictional clients that includes a demonstration of the prototype and the program they've created in action. The student scenario is followed by the daily plan. And the daily plan acts as a roadmap of sorts, and it clearly lays out the expectations as students work through the projects in the student scenario. Each day of the plan acts as a guideline to spell out specifically what the students will look at that day and what they're going to need to accomplish. Now, you'll see that as different concepts are addressed, students are provided with helpful links, which will give them more information. For example, they're going to have links showing them what's going to be required in a design brief that they're being asked to create and maintain, or what kind of information they're going to need to track in their digital engineering journal, or perhaps how to install and use the RoboPro programming software. And we're going to take a look at some of these links just a little bit later. But again, each day of the plan contains a different task to be addressed, a different activity to perform, or a different question that needs to be answered. As an example, if you look closely at the bottom of the page on day 7 here that I have on the screen, you're going to see that there's a discussion topic, which is, how does my dishwasher know when the dishes are clean? Well, of course, a dishwasher doesn't judge or comprehend when dishes are clean, but instead it's programmed a certain way to go through certain cycles for a specific period of time. So in this case, the teacher can lead a discussion where this idea can be explored further. Now, other things covered in this unit, for example, include how data is taken from a sensor and recorded, or how files can be taken from the RoboPro format, put into an Excel format to be worked on, and then put back into RoboPro, or, for example, working on robotic positioning. Now, this happens to be one of the longer units of the curriculum, and it continues for a period of 35 days total. Now, getting back to it, as students work through the daily plan and on their answer to their student scenario, once again, they're going to be required to perform research. They're going to be required to do trial and error experimentation, and again, document the entire process. And this means maintaining a design notebook and a digital engineering journal. They're going to design and build a working prototype, again, using Fischertechnik. And if the model is automated or robotic, as it is in this case, being an elevator, students will also have to design the program that controls that particular model. Now, putting everything together, each student group will, at the end of each of these units, create and deliver a presentation of their prototype in action. And the idea during the whole course of this is that each day builds on the day before it, and each activity is subsequently more complex, and along the way will provide more of the information that students will need to draw on to successfully complete the project they're working on. And overall, it's designed to really help and reinforce the concepts and tie everything together in a very organic and meaningful manner. Now, there are also various supplemental materials included at the end of each of these project units. Now, depending on the particular unit, this could include vocabulary words. It could include carefully selected web-based resources. It might include Word documents, PDF files, PowerPoints, what have you. And once again, each unit of the curriculum for both the STEM Prep 2.0 and the STEM engineering sets follows the same structure as we've just seen, including the standards, the rubrics, the daily plan, the resources, and so on. And as I mentioned before, there are also numerous links throughout the curriculum designed to provide more guidance on specific topics as they come up. Now, besides being linked this way throughout the curriculum, these sections are also collected in one place at the end of the curriculum here. Now, once again, using the STEM engineering curriculum as an example, there are links provided detailing information on things such as what's required in a design brief, what's required in an engineering notebook. There's a section on schematic drawings, another on Ohm's law and power, a section on how to program a robot to detect motion using the camera attachment, working with digital branching, working with flowcharts, working with open and closed loop programs, working with combinational logic, working with the RoboPro software, robotic positioning, working with sensors, working with data, using vision systems, subprograms, and so on. Now, there's also a section where all of the rubrics of the curriculum are collected, both the general course rubrics as well as the specific rubrics for each individual project theme unit. And finally, this is followed by a section containing the step-by-step assembly instructions that I had mentioned before. Once again, the STEM prep curriculum will follow the same structure, just with a focus, of course, on some different subject areas. Now, I'd like to share a few photos with you of one of the schools currently using the Fischertechnik STEM Prep 2.0 and STEM engineering sets. And this particular school is Westfield Technical Academy, located in Westfield, Massachusetts. Now, the program there is being conducted by Dave Roberts, who is the science teacher at Westfield. Now, what you see in these pictures are the students as they address the first hands-on challenge presented in the curriculum for the STEM Prep 2.0 set, and that is of designing and building a prototype of a braking system, such as would be found on a racing bicycle. Again, students work in small groups. With the STEM Prep 2.0, we do recommend one set per each group of 2 students. But again, with the STEM engineering set, because of the nature of the projects being more involved, you could expand that group up to even 3 or 4 students. And as you will see from the photos, while the students are all working on the same project, there is no one right way, no single solution for addressing the design challenge given in each unit student scenario. As such, some of the students will create and build prototypes that work smoothly and efficiently, and others might design models that clearly more refinement to be practical. But in any case, the goal is, of course, to see how well the students synthesize all the concepts they've learned and how working in small teams, how well they can use their creativity and their problem-solving skills to make something that will most effectively and efficiently answer the criteria given in the student scenario. Now, I'd also like to mention another benefit of the STEM Prep 2.0 and STEM engineering sets, albeit it's a somewhat unintentional benefit. Now, as I found out, a large segment of the students at Westfield Technical Academy are what would be classified as ESL students, which is, of course, English as a second language. And in this case, these are students who originally came to the US from Russia and the Ukraine. Now, in Massachusetts, teachers are required to take classes in ELL, which is, of course, English language learning, to help meet the needs of these particular students. Now, Dave Roberts, who, as I mentioned earlier, is the teacher in charge of the Fischertechnic STEM programs at Westfield, told us that he has attended 3 different ELL training classes. And all 3 of these ELL training classes in particular highlighted project-based learning as an important learning tool for ESL students. Now, the reason given is because design is really sort of a universal language. And working through the curriculum in this hands-on fashion helps to not only teach the students essential STEM-related concepts, but it also aids in building their English language skills because it helps to make the connection to actual processes and actions they can understand. Now, again, I've shared here is just a sample of some ways students can address this particular design challenge. Now, as I've stated before, each subsequent unit will require more sophisticated designs, and each will again build on what has come before. So just to very quickly summarize what we've covered, each Fischertechnik STEM Prep 2.0 and STEM engineering set contains everything you're going to need. It contains all of the parts, the software, all the assembly instructions, and the complete day-by-day curriculum. And the curriculum included in each set is yours to use this year, next year, and we would, of course, hope for many years to come. There are never any additional fees or subscription charges involved. Everything you need is included. And again, it's all reusable. You can build a model, perform the experiments, take it apart, and you're ready to build another. And of course, if you ever did need any odd spare parts, or if you did need replacement pieces, you can purchase these individually in whatever quantity you choose or need directly from the Studica website. Again, the Fischertechnik STEM Prep 2.0 and STEM engineering sets are designed to make it easy for educators from all backgrounds to offer a hands-on project-based learning experience to their students. Once again, project-based learning is what experts agree is one of the most effective methods known for teaching STEM concepts. Again, the STEM Prep 2.0 set comes with over 2,200 parts and components, day-by-day project-based curriculum PDFs for both students and teachers, and over 75 hours of academic material, as well as step-by-step assembly instructions from 9 popular Fischertechnik education sets for building 118 different models. The pricing on this set starts at just $899 per set, with classroom pricing available upon request. And the STEM engineering set shown here includes 890 parts and components, including programming software, the full-color touchscreen TXT controller, sensors, motors, and much more, as well as student and teacher curriculum PDFs featuring over 150 academic hours of material, and full-color step-by-step assembly manuals from the 3 most popular Fischertechnik robotic sets. Pricing on this set starts at just $939 per set, and again, please contact us directly for classroom pricing. So at this point, if you have any questions, and I haven't seen anything pop up yet, but if you did have any questions, I would ask you to type them into the chat window or the question and answer window, both of which you can find on the Zoom toolbar. if you don't have any questions, I'll just keep things moving along. I just want to get you these numbers. If you do have any questions, if you'd like to speak to us directly, if you'd like to request a quote, or if you'd like to speak to the dedicated educational representative for your state, you can call us directly. The number here at Studica US, toll free, is 888-561-7521. If you happen to be located in Canada, you can call the Studica Canadian office at 800-561-7520. You can also find out more about all of the Fischertechnic education solutions, including the STEM Prep 2.0 and the STEM Engineering Set, by visiting our website at www.studica.com/Fischertechnic-education. And of course, you could email us with any questions you might have at info@studica.com, STUDICA.com. So on that note, if you don't have any questions, I'd like to thank you very much for taking the time to attend today. We look forward to hearing from you soon. Have a great afternoon.